Hi, period 3. I hope you all had a good Memorial Day weekend. I am out today with strep throat, and I will be back tomorrow. The doctor said I won't be contagious anymore today. We're going to leave quadratics now, and we're going to do some probability because it will be on your EOC2 that you have to take. So I want to make sure that we spend some time on it. And we're going to start today with talking about the counting principle and permutations. I'd like you to have your grid composition book out and a pencil, and I'd like you to be ready to take notes. I'd also like Lauren to come up and sit at the computer because there are going to be times when I ask you to pause the video, and I don't know who your sub is today, so I don't know how much the sub can help you with math, but hopefully I've done a good enough job that you won't have too many questions. For now, please don't worry about your quadratics test that you began on Friday. When I come back, I will make arrangements for you if you need a little bit more time, but for now, just don't stress about it. If Lauren is not available to come up and work the computer, she's gone today, then instead I would like to have Jessica come up and do that for me today. Okay, so by now your grid composition book should be out and you should be ready to go. We're going to start today with the counting principle. And the counting principle is to help you deal with the occurrence of more than one event or activity and to be able to do it quickly so that you can determine how many possible outcomes exist. You don't have to use the counting principle to figure out how many outcomes exist, but it certainly is the quicker way. Let's talk about this example. So if ice cream sundaes come in 5 flavors with 4 possible toppings, how many different sundaes can be made with 1 flavor of ice cream and 1 topping? So just quickly, let's think about that. If we have vanilla and chocolate and cookie dough and orange sherbet, even though I don't know that that's an ice cream, as our 4 types, and then maybe some M&Ms and some sprinkles and some chocolate chips and some coconut shavings, my favorite. Well, you could have vanilla ice cream with coconut shavings, and you could have chocolate ice cream with coconut shavings, and you could have sherbet with coconut shavings, and you could have cookie dough with coconut shavings, and now we have 4. The counting principle is meant so that we don't have to list all of those out. And so rather than list the entire sample space, which just means all the different possible combinations, we simply multiply 5, which is the number of ice cream flavors that you had, times 4, the number of possible toppings that you had, and 5 times 4 is 20 possible sundaes. This simple multiplication process is known as the counting principle. Now, what should go in your grid composition book is counting principle, and this part right here. If there are A ways for one activity to occur and B ways for a second activity to occur, then there are A times B ways for both of those to occur. And Lauren, I'd like you to push pause, and I'd like the substitute teacher to walk around and just make sure that everybody has that copied into their grid composition book. Okay, let's do some examples. Our first one is, what if we were looking at rolling a die, a standard die, with the numbers 1, 2, 3, 4, 5, and 6, and flipping a coin, so you have heads or tails. Since there are 6 ways to roll a die and 2 ways to flip a coin, 6 times 2 equals 12. Okay? What about if we draw 2 cards from a standard deck of 52 cards without replacing the cards? Well, there are 52 ways to draw the first card, and there are 51 ways to draw the second card. And the reason that we've lost a way is that we didn't replace that first card. So now, instead of 52, we only have 51. And so now if we multiply using the counting principle, 52 times 51 is 2,652 ways to draw the 2 cards. Now, the counting principle can also work for more than just 2 activities. What if a coin is tossed 5 times? Well, there are two ways to flip each coin. So even if it's the same coin, we're talking 5 different events going on there. There's going to be 2 times 2 times 2 times 2 times 2 equals 32 arrangements of heads and tails you could possibly get if you flip a coin 5 times. What if a die is rolled 4 times? Well, now there's 6 ways to roll each die. And so we have 6 times 6 times 6 times 6 equals 1,296 possible outcomes. What I'd like you to do is I'd like you to not copy these examples down. So at this point you were just listening because you'll get a chance to practice here in a couple minutes. Make sure though that you understand what's going on. Okay, so let's do this practice problem, and on this one what I'd like you to do is I'd like you to write the answer in your grid composition book and stand up when you have your answer so that Lauren will pause after this has been read, and then she will start it again when everybody is standing. Okay, so before you get started here, a movie theater sells 3 different sizes of popcorn, small, medium, and large, with 3 choices of toppings: no butter, butter, and extra butter. How many possible ways can a bag of popcorn be purchased? Lauren, you go ahead and pause, and everybody stand when you have the answer. Okay, so what you should have done here is taken the 3 sizes and multiplied by the 3 choices of toppings: no butter, butter, extra butter, and 3 times 3 is equal to 9. That means that there are 9 different ways that a bag of popcorn can be purchased. Okay, information about girls' ice skates. You have colors: white, beige, pink, yellow, and blue. You have sizes 4, 5, 6, 7, and 8. And you have extras: tassels, striped laces, and bells. Assuming that all skates are sold with 1 extra, how many possible arrangements exist? So Lauren, you're going to go ahead and push pause. So for this one, you should have done 5, the number of color choices, times 5, the number of size choices, times 3, the extras that you can add to your skates, and this time the correct answer would be 75. Your state issues license plates that consist of letters and numbers. There are 26 letters, and the letters may be repeated. There are 10 digits, and the digits may also be repeated. How many possible license plates can be issued with 2 letters followed by 3 numbers? Okay, Lauren, go ahead and pause. So I put little slots for the different spots that you would have on your license plates. You're going to have 2 letters followed by 3 numbers. And because it said that both the letters and the numbers can be repeated, there are 26 choices in the first slot, and there are 26 choices in the second, and then 10 in the third, 10 in the fourth, and 10 in the fifth. And when you multiply all of those, you get 1,757,600. Okay, an ice cream shop offers 31 flavors. You order a double scoop ice cone. In how many ways can the clerk put the ice cream on the cone if you wanted 2 different flavors? Okay, pause. Okay, so since there's 31 flavors and you don't want the same flavor for your 2 scoops, on your first scoop there's a possible 31 choices, and on your second scoop there's only 30 flavors possible, and 31 times 30 equals 930 different ways the clerk could put ice cream on your cone. Heather has finally narrowed her clothing choices for the big party down to 3 skirts, 2 tops, and 4 pairs of shoes. How many different outfits could she form from these choices? Lauren, pause. So this time I'm going to multiply 3 for the skirts, times 2 for the tops, and 4 for the pairs of shoes. And 3 times 2 is 6, times 4 is 24. Okay, Burger Queen, instead of Burger King, offers 4 types of burgers, 5 types of beverages, and 3 types of desserts. If a meal consists of 1 burger, 1 beverage, and 1 dessert, how many possible meals can be chosen? Lauren, go ahead and pause again. So since I have 4 burgers and 5 drinks and 3 types of desserts, 4 times 5 is 20, times 3 is 60 possible meals that can be chosen. Okay, so Kyle has 5 tank tops, 3 pairs of jeans, and 2 pairs of sneakers. How many different outfits consisting of 1 tank top, 1 pair of jeans, and 1 pair of sneakers are possible? I'm going to go ahead and pause. So 5 tank tops times 3 pairs of jeans times 2 pairs of sneakers, excuse me, equals 30 possible outfits that Kyle can make. So now we're going to switch topics away from the counting principle, although we will continue to use it, and we're going to talk about permutations. And so now I'm going to want you to start a new section in your Good Comp book. You don't need to go to the next page or anything, but I do want you to write down permutations, and I want you to write down this definition. Excuse me. A permutation is an arrangement of objects in specific order, meaning that the order of the arrangements is important. Make sure you wrote that down. A permutation is an arrangement of objects in a specific order. So consider 4 students and they're walking towards the school entrance. How many different ways could they arrange themselves in this side-by-side pattern that they have? Well, we could have it be person 1, 2, 3, and 4, or we could go 1, 2, and have 4 and 3 switch, or we could go 1, 3, and 2 and 4, and so on. There are 24 different combinations, and you'll notice that there are 6 combinations with 1 in the lead, and 6 with 2 in the lead, and 6 with 3 in the lead, and 6 with 4 in the lead. This reminds me of the problem on the MSP practice with the, I believe it was the spades, the clubs, the diamonds, and the hearts, and asking how many combinations with the hearts in the first position. And it's exactly like this problem. So we see our 24 different combinations here, but they're showing you that a quicker way to do that is to do 4 factorial. And we're going to talk about what that means in a minute. 4 factorial, which means do 4, the number in the first position, times 3 times 2 times 1. There's 24 different arrangements or permutations of students walking side by side. Now I talked to you a little bit about factorial notation. That was that 4 with the exclamation mark. This time it's 5 with the exclamation mark. Factorial notation is used when you need to work with a series of factors, each being 1 less than the previous factor. So instead of writing out 5 times 4 times 3 times 2 times 1, we use factorial notation and we write 5 factorial equals 120. Now, this is interesting. I'm going to show you why in a minute. 0 factorial is equal to 1, and 1 factorial is also equal to 1. Let's look at why. So the idea of factorial in simple terms is to use to compute the number of permutations or combinations of arranging a set of numbers. So let's think about if you were arranging 1. Well, there's only one way to arrange 1. Okay, so that's why 1 factorial is 1. And if you were looking at 2, well, you could have a combination of 1, 2, and you could have a combination of 2, 1. In other words, there are 2 ways to list the number 2 in order of arranging a set of n numbers. So if you have 2 numbers, 1 and 2, there's 2 ways to arrange them. If you have 3 numbers, 1, 2, and 3, you could do 1, 2, and 3, 1, 3, and 2, 2, 1, and 3, 2, 3, and 1, 3, 1, and 2, and 3, 2, and 1. There are 6 different ways to do that. Now, if you were writing that out, you'd go, in factorial, you'd go 3 times 2 times 1, or 3 factorial, 6 different ways. And this is 2 factorial, and this is 1 factorial. And so if you were doing 10, well, you could do, the first combination would be 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. And then you could have a whole bunch of different combinations. In fact, 3,628,800. And that would be 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Different ways, or 10 factorial. So therefore, if you're looking at the ways to arrange 0, well, it can be said that an empty set, okay, an empty set, there's your empty set, can only be ordered one way, so 0 factorial equals 1. And that's something important for you to remember. 1 factorial equals 1, and 0 factorial equals 1. Okay, let's move on. More permutations. And remember that permutations are just ways of arranging different things. In this case, it was all numbers. Okay, so we have some notation for permutations, and this I'll want you to get down. And the notation is N and then PR. Now your N represents the total number of objects, and R is the number of objects chosen. And I want you to go ahead and record this in your grid comp book. Okay, so now you've got the number of total objects, and you have the R is the number of objects chosen, and the way you're doing this is you're going to go N times N minus 1 times N minus 2, which really means you're doing factorials. For instance, if this was 8P8, this would be 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, because there's 8 objects and you asked to do all 8. And the n minus 1, n minus 2 is because the first number was 8, and then 8 minus 1 is 7, and 8 minus 2 is 6, and so on. That's what they're showing you there. They're also showing you over here that another way to do it, and you're going to see both, they're going to show you these in examples, is to do n factorial, okay, that's the number of objects, divided by n minus r, where remember r is the number of objects chosen or wanted. Okay, so let's go on to the next one. So here are some examples that we have now. And what I'm going to do is I'm going to give you a little bit of time. I want you to record these in your grid composition book, so you're recording each of the notations, because this is a different notation that you're not used to writing in, and then the answer as well. You're working your answer, so you have something to remember this. It's like you're taking notes and you're making sure that you have some examples to look back at. So it says to compute 5p5, and I want you to remember that that means that you have 5 things, and they're asking you to arrange 5 ways. Okay? And so I'm going to show you what that would look like. Use our magic eraser here. So that would tell us to do 5 times 4 times 3 times 2 times 1. Notice that we started with 5, and then it tells us to do all 5, 1, 2, 3, 4, 5. If this was a 2, I would have done 5 times 4. But because it told us to do all 5 times 4 times 3 times 2 times 1, which is 120. Okay, let's look at the next one, 6p2. Now I helped you with the last one, so this time I want Lauren to pause and I want you to copy the problem, 6p2, write your work down, write the answer, and stand when you're ready. So you see here, I left you a hint. This 2 is telling you that you're not going to do 6 times 5 times 4 times 3 times 2 times 1. You're only going to multiply by 2 factors of the factorial starting at the 6. So here we go. Let's see how you did. Now, remember that before on the previous page, I was showing you that there were 2 ways that you could use the factorial notation that we looked at in the beginning. So it's 6 times 5 times 4 times 3 times 2 times 1. Or you could do this one here where it's showing you do the factorial and then divide by n minus r. So now I'm going to show you what that would look like over here with the eraser. Okay, the perfect problem for this. So we know that 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. And then on the bottom, I'm taking this 6 and subtracting 2 because I only want those 2. I only want 2. Well, 6 take away 2 is 4. So what I'm really doing is 4 factorial. Notice that the factorial is outside of the parentheses. Well, so 4 times 3 times 2 times 1 is 4 factorial. And notice that these are canceling. 4 divided by 4, 1. 3 divided by 3, 1. 2 divided by 2, 1. 1 divided by 1, which means I still end up with the 6 times 5 is 30. Okay, let's look at number 3. Find the number of ways to arrange 5 objects that are chosen from a set of 7 different objects. 5 objects that are chosen from a set of 7 different objects. Lauren, pause. Okay, so let's see how you did. So notice first that they put it in notation for you. So the first 2 times they wrote that for you. This time they were expecting you to be able to write it. If you didn't put it in your grid comp book, please. So 7 is the 7 different objects, but we're only arranging, we're finding the number of ways to arrange 5 of those objects. That means we're doing 7 times 6 times 5 times 4 times 3. Only the first 5 of 7 factorial. 1, 2, 3, 4, 5. And if you multiply 7 times 6 times 5 times 4 times 3, you get 2,520. Looking at it the second way, you can also do 7 factorial divided by 7 minus 5 factorial. So this time it's 7 factorial, and 7 minus 5 is 2 factorial, which is written 2 times 1. These are going to cancel, and I'm still left with 2,520. Make sure that you're writing these things down. Make sure you know both ways of doing this, that you're comfortable with them. Make sure that you're comfortable with reading a problem now and writing it out in this notation yourself. What is the total number of possible 5-letter arrangements of the letters white, W-H-I-T-E, if each letter is used only once in an arrangement? Lauren, pause. Okay, so this time we have 5P5 because we have 5 arrangements and we have 5 letters. So this time we're doing 5 times 4 times 3 times 2 times 1, which is 120. Or we're doing 5 factorial over 5 minus 5 factorial, and 5 minus 5 is 1, and 1 factorial is 1. Remember, 0 factorial is 1, and 1 factorial is 1, which is still 120. You notice they could have done that up here, but they didn't. They didn't show you that second way on this one, but these 2 problems are really exactly the same thing. Number 5. How many different 3-digit numbers can be made from the digits 4, 5, 6, 7, 8 if a digit can appear just once in a numeral? 3-digit numerals can be made from the digits 4, 5, 6, 7, 8 if a digit can appear just once in a numeral. Lauren, go ahead and pause. Hopefully you're starting to feel like you've really got this now in terms of what to write and then how to do the math. So this time we're only looking at 3-digit numbers, how many different 3-digit numbers, so that's what I want. And again, I have 5 digits, so I'm doing 5p3, and that's 5 times 4 times 3, which is 60, or 5 factorial over 5 minus 3 factorial. 5 minus 3 is 2, and so that'd be 2 times 1. These cancel, and I get 60 either way. Okay, so in this example, we have 2 parts to it, and we're going to do part A, and then we'll do part B. And you don't need to hit pause this time, Lauren. We'll just go ahead and go through it. So here's our situation. Using the letters in the word square, tell how many 6-letter arrangements with no repetitions are possible if, and our first situation is going to be if the first letter is a vowel. Now, if you think about the vowels that are in the word square, we have a U, we have an A, and we have an E. All the other letters are consonants. So when working with arrangements, it's often helpful, you've seen me do this, to put down lines to represent the locations of the items. For this problem, 6 locations are needed for the 6-letter arrangements that they talked about. So again, I'm trying to use those letters to tell how many 6-letter arrangements with no repetitions are possible if your first letter is a vowel. So 1, 2, 3, 4, 5, 6. Now they gave me a parameter for this first location, and that is that it has to be a vowel. Well, there's only 3 vowels, so that means that I have 3 choices to fill in the first location. And then after the vowel has been placed there, there are 5 letters left to be arranged in the remaining 5 spaces. So now I'm doing 5 factorial. 5 times 4 times 3 times 2 times 1. Okay, so there's 2 ways that I could write that. So the first thing to think about is how this and this are kind of like 2 different parts here. I didn't need to get the word or in there. And what I'm looking at is this 3 and then times, well, I already know how to write 5 factorial, right? You've got a 5, a p, and a 5. And so if you were doing that mathematically, your answer would be 360. So the answer to the question, how many 6-letter arrangements with no repetitions are possible, there's 360 of them. Now I'm working on part B, and part B says how many 6-letter arrangements with no repetitions are possible if vowels and consonants alternate beginning with a consonant. Okay, so let's take a look at that situation. So I still have 6 locations needed, and beginning with the consonants. So interestingly enough, square has the same amount of consonants as it does vowels. So I'm still starting with this 3 here. And then every other location is filled with a consonant. Well, remember, I'm not allowed repetitions here. So this is going to be a vowel, right? This is a consonant, but there's only 2 left now. And this is a consonant, there's only 1 left now. And then now if you go back, there's, beginning with the vowels here, there's 3 vowels, and then there's only 2 vowels, and then there's only 1 vowel. And so this time, I'm doing a different problem. I'm doing 3 times 3 times 2 times 2 times 1, which comes out to be 36. A lot less repetitions, a lot less arrangements altogether, because there are so many parameters with alternating every other consonant like that. Okay, So now we're going to take a look at probability and permutations, and we're kind of combining some things. So this section of your grid comp book, you should head probability and permutations. So some things to remember here. When dealing with probability and permutations, it's important to note if the problem deals with replacement or without replacement. For example, with replacement would be drawing an ace from a deck of cards and then putting the ace back in the deck before drawing a second card. Without replacement would be drawing the ace and not replacing it in the deck before drawing the second card. Don't forget to use the counting principle for compound events. It's fast and easy. And here's our probability formula. You've been using it forever. You're doing the number of the number of elements. S is the number of elements in the space, and the number of outcomes in the event is your numerator. Okay, so you've got two cards and they're drawn from random from a deck of 52 cards without replacement. What's the probability both cards drawn will be queens? Well, first they're showing you that you have, in the notation we've been using, 4p2, and that's because there are 4 times 3, which is 12. Okay, two cards are drawn from a deck, and we're looking at 4 queens, and we're doing it without replacement. 4 queens out of 52. And so 4 times, that's what's on the top, 4 times 3, because you're only looking at drawing it twice. Okay, if you're drawing all 4 cards without replacement, then this would be 4p4. But it's only 4 times 3, or 4p2, because you're only drawing twice without replacement. Now, the total number of cards in a deck is 52, and you're drawing twice, so this is going to be divided by this, and 52 you didn't replace, so now there's 51, and so 12 over 2,652 reduces to 1 over 221, and yes, you should always reduce. So again, I want you to think about this. If you were drawing all the queens, instead of 2 cards, it was 4. If 4 cards were drawn at random from a standard deck of 52 without replacement, this would be 4p4, and then this would be 52p4, and this would be 52 times 51 times 50 times 49. Okay, Mrs. Schultzke has to correct papers for 3 different classes: algebra, geometry, and trig. If Mrs. Schultzke corrects the papers for each class at random, what is the probability she corrects algebra papers first? There is only one way to correct algebra papers first, and then there are 2p2 ways to correct the other 2 sets of paper. The total 3 sets of papers, 3p3. So they're showing you that you have 1 times 2p2, because there's only one way to correct the algebra papers first, divided by 3p3. So 1 times 2 times 1, and 3 times 2 times 1, which is 1/3. And make sure that if you need Lauren to pause this page, that you ask her, so that both examples, that you have them down. I would even be making sure that I get this stuff so that you know what it came from. You know, this was the 4p2 represents the way to draw 2 cards of 4 possible queens, and the total is the number of the ways to draw 2 cards from a deck of 52 cards. So make sure you're getting it. Ask her to pause whenever you need her to. Number 3, a card is drawn from a deck of standard cards and then replaced in the deck. A second card is then drawn and replaced. What is the probability that a queen is drawn each time? Okay, so this time we're not keeping the cards out. So if you're talking about two cards being drawn. This time, the both total cards is 52, and there are 4 ways to draw a queen each time. So on the first draw, you have 4 out of 52 chances of drawing a queen, and on the second draw, 4 out of 52. I'm using the counting principle now and multiplying those two things for 16 out of 2,704, which reduces to 1 over 169. Okay, let's try some practice problems here. This first one, I think what I'm going to do here is just have Lauren pause after each one so that you can talk about it. And so your first one is to evaluate 4 factorial. So go ahead and write the problem down and the answer and stand up when you're ready. Okay, so hopefully you gave this a try. This 4 factorial is asking you to do 4 times 3 times 2 times 1, which comes out to be 24. Okay, let's try the second one. Go ahead and write it down. Lauren, hit pause, and you can start it again when everyone is standing. Okay, so this one's asking you to do 9 times 8 times 7, and if you did that, you'd get 504. Okay, this one you shouldn't need for a pause for because we talked about this 0 factorial equals 1. Okay, let's have you do the last one, write it down, show the work, stand up when you're ready, and Lauren, go ahead and hit pause. Start again when they're standing. So on this one, 6 factorial is 6 times 5 times 4 times 3 times 2 times 1, which comes out to be 720. And 6 times 5 is 30, and when you divide those two, you get 24. Okay, let's go to the next page. How many different 5-letter arrangements are there of the letters in the word digit? Go ahead and write your work, and when everybody is standing, Lauren, you can start it again. Go ahead and pause. Okay, now this one is very different because initially it starts out as 5P5. How many 5-letter arrangements can you make in the word digits? Digit has 5. So that's where the 5P5 comes from. 5 arrangements, and then there's 5 letters in the word digit. The 2 factorial on the bottom comes because in this case there are 2 letters here that can repeat. So to account for those, we want how many different 5-letter arrangements, but these 2 are repeating. We divide by the 2 factorial, so the 2 i's that are repeating. So we're really doing 5 times 4 times 3 times 2 times 1, and then once we've done that, we have to do divided by 2 times 1. And if you do 5 times 4 times 3 times 2 times 1, whoopsies, you're not going to get 0. I did the wrong thing on the calculator, so hold on. 5 times 4 is 20, times 3 is 60, times 2 is 120, all right? And then we're dividing that by 2, because 2 times 1 is 2. And when you divide that by 2, you get 60. Okay, let's do the next one. And again, Lauren, you'll start it again when everybody is standing. If a 3-digit number is formed from the digits 1, 2, 3, 4, 5, 6, and 7, with no repetitions, how many of these 3-digit numbers will have a value between 100 and 500? Okay, give this a good shot and stand up when you're ready. Okay, so we have the digits 1, 2, 3, 4, 5, 6, 7, and we need 3 locations if we're forming a 3-digit number. In the 100s, the 200s, the 300s, the 400s, etc. All those 3-digit numbers have 3 locations. So to be between 100 and 500, the hundreds place must be the digit 1, 2, 3, or 4. Which means that if the hundreds place is 1, 2, 3, or 4, then there are 4 possible ways to fill in that first location. It could be a 4, it could be a 3, it could be a 2, or it could be 1. Then there are 6 digits left, because remember it said no repetitions. 6 digits left to arrange in the remaining 2 places. So, 2 places. So here's my notation this time. I'm doing 4. That's the number of different possibilities, 1, 2, 3, or 4, in that first spot in my 3-digit number. And then, since there's 6 digits left to arrange in the remaining 2 locations, I'm doing 4 times 6p2. Well, 6p2 really just means 6 times 5. And 6 times 5 is 30. And 4 times 30 is 120. Okay, let's take a look at the next one here. This next one says, if the letters in the word triangle are rearranged at random, find the probability that the first letter is an A. Go ahead and pause, Lauren. Give people a chance to work on that. Okay, so there's one way to get an A, and then there are 7p7 ways to arrange the other letters in the word triangle out of a total of 8p8. So our solution is 1 times 7p7 divided by 8p8. And so down here what you're seeing is the 1 over 8, and then because 7 times 6 times 5 times 4 times 3 times 1 over 7 times 6 times 5 times 4 times 3 times 1 cancels, we have a total of 1/8. Okay, let's look at number 8. 2 cards are drawn at random from a standard deck of 52 cards without replacement. What is the probability of drawing a 7 and a king in that order? Lauren, go ahead and pause. Okay, it says a 7 and a king in that order. There are 4 7s and 4 kings. So we have 4p1 and 4p times 4p1 from a deck of 52 cards, 52p2, because we want 2 cards. It says we're going to draw 2 cards at random. So 4 times 4, and that comes from multiplying the 4p1 times the 4p1. So 4 times 4 is 16, and 52 times 51 is 2,652. And if we reduce this, that is 4 out of 663. Here, our last problem says, throughout history, many people have contributed to the development of math. These mathematicians include Pythagoras, Euclid, I think that's Hypatia, Euler. I know it looks like Euler, and a lot of people pronounce it Euler, but I looked it up one time and it's pronounced Euler. Einstein, Ignacy, Fibonacci, and Pascal. What is the probability that a mathematician's name selected at random from those listed will start with either the letter E or A? This one doesn't require any fancy mathematics because you're just looking at the probability from a selection there, and there's if you count the ones that have a E or an A here, we have 1, 2, 3, 4, and there were 8 total. 1, 2, 3, 4, 5, 6, 7, 8, and so 4/8 is the correct answer on that one, which should have been simplified to 1/2, because you will rarely see probability that's not simplified. Number 10, there are 12 horses in a horse show competition. The top 3 winning horses receive money. How many possible money winning orders are there for competition with 12 horses? Lauren, go ahead and pause and let people work. So hopefully you saw that as 12p3, and I think I wrote that incorrectly. It should have been a big P with a little 12 and a little 3. That's okay, you're allowed to make mistakes when you have strep throat. And so I'm doing 12 times 11 times 10, and if you did that, 12 times 11 is 132 times 10 is 1,320. One more. How many different 4-letter words can be formed from the letters in the word math? And I hope you are thinking that that's going to be 4 factorial, 4 times 3 times 2 times 1, or 12 times 2 is 24. Okay, now homework. I know you're excited about this one. For homework, the first thing I want you guys to do is open your books to chapter 6. And in chapter 6 today we've talked about the topics of the counting principle, and we've also talked about permutations. I don't know, because I do not have my math book home with me, what sections in chapter 6 the counting principle and what section was permutations, but I would like you to find, and I want you to agree to it as a class so we're not all doing different problems. Find the section on the counting principle and find the section on permutations, and I'd like you to do a total of 8 problems from 8 sections from the practice exercises, making a total of 16, but you need to agree on which practice problems you're doing, so everybody is doing the same problems. It would be great if somebody could post me what the homework problems were, because then I'll post the notes to Edmodo, and I will also then make sure that I record the homework assignment. I hope you did a good job today, as you always should be doing for a guest teacher, and I will see you tomorrow. Bye-bye.